Soil science and the global context. Soil, a critical but threatened resource. The scientific community recognizes soil as a non-renewable resource on human timescales. The International Union of Soil Sciences launched the 2025-2034 Decade of Soil Science to prioritize research, policy linkages, and public understanding around soil health and management, recognizing that soil degradation threatens food systems and ecosystem services globally. Global soil degradation alarms. UNESCO and other international bodies warn that up to 75% of land worldwide is degraded. Soil degradation directly threatens food production and ecosystem functions. Erosions, compactions, loss of organic matter, and chemical pollution are key drivers of degradation. Adoption of practices like permanent soil cover, organic matter addition, and reduced tillage, core green farming methods are scientifically recommended to counter these trends. Implication for green farming. Sustainable practices directly align with what scientists identify as the most effective structural solutions to degradation. Water science and agriculture under climate stress. Declining land water storage. A recent science study using multiple data sources found that the Earth has lost over 2,000 gigatons of water stored on land, including soil moisture, largely due to climate change. This loss affects agricultural system by reducing available water for crops, intensifying drought impacts, exacerbating irrigation pressure, and soil desiccation. Scientists compare this shift to an arrhythmia in the Earth's hydrological cycle, a serious signal that water stress is becoming systemic. White matters to green farmings. Techniques such as improved soil structure, organic matter enhancement, and water retentive management are not optional. They are scientifically essential adaptations. Reducing water pollution through sustainable practices. Scientific reviews show that sustainable practices reduce runoff nitrates and phosphates, lower pesticide contamination in water systems, enhance soil water holding capacity. These outcomes aren't anecdotal. They are documented across multiple ecosystems, linking reduced chemical inputs and ecological balance with measurable improvements in downstream water quality. Technology and innovation in sustainable agriculture. Precision and intelligent systems in farming. Cutting-edge research is exploring the use of AI, machine learning, and intelligent control systems to balance productivity with environmental protection. One study used reinforcement learning to optimize nitrogen use and irrigation, reduce nitrous oxide emissions, improved adaptability to climate variability. This represents a scientific convergence between ecology and digital innovation in agriculture. Novel green technologies. Experimental research into technologies such as plasma agriculture, which uses non-thermal plasma to enhance nutrient availability and seed germination, points toward future tools that could boost plant growth with minimal environmental cost. This demonstrates that green farming isn't anti-technology. It leverages innovation to serve sustainability. Policy innovation and European frameworks. The European Union's common agricultural policy now explicitly integrates sustainability goals, structuring environmental objectives into economic incentives, research support, and policy frameworks. CAP aims to enhance biodiversity, protect natural resources, soil, water, and air, encourage low-input agriculture, support innovation and adoption among farmers. This institutional change reflects scientific consensus. Sustainability is not just beneficial, it is imperative for food systems. Linking practice and research, global to local. Across the world, from policy programs in the European Union to national awards for sustainable agriculture innovation, in India, there is scientific and applied evidence that minimal tillage and organic inputs improve resilience. Water management innovation increase yield stability. Technological integration enhances resource use efficiency. Scientific programs like the European Innovation Partnership for Agricultural Sustainability actively connect researchers and farmers to translate research findings into field practice. Implication for education and practice. Green farming research emphasizes in interdisciplinarity, combining ecology, soil science, hydrology, economics, and social science. Long-term studies benefits often emerge over decades, not season. Scale awareness benefits differ between field, regional, and landscape scales. These insights should shape how agriculture is taught, practiced, and supported, especially in regions experiencing climate stress. Scientific consensus on green farming. The scientific record is clear. Sustainable agriculture enhances soil health, water quality, biodiversity, climate resilience and long-term productivity. Diversification and ecological practices deliver ecological and economical benefits over time. Soil protection, water conservation, and biodiversity are validated as essential by both experimental studies and policy frameworks. As students and future professionals, understanding the science behind green farming equips us to design, evaluate, and improve agricultural systems that work for both people and for the planet. Principles of green farming: healthy soil. Soil is a living organism. Green farming improves soil fertility using compost, earthworms, manure, mulching, crop rotation, cover crops like clover and legumes. Healthy soil retains water and grows stronger, more resilient plants. Water conservation. Water is limited. Sustainable farms use drip irrigation, rainwater harvesting, shaded soil to reduce evaporation, crops suited to local climate, biodiversity. Diverse farms are healthier farms. Green farms grow multiple crops, maintain natural habitats, plant flowers to attract pollinators, include trees for shade and erosion control, natural pest and weed control. Instead of chemicals, ladybugs eat aphids, birds eat insects, basil, garlic and mint repel pests, mulch prevents weeds. Reduction of chemicals. If chemicals are used, they are minimized and applied responsibly. Method key idea example: organic farming, no chemical fertilizers or pesticides. Organic vegetables farm. Permaculture farms designed like natural ecosystems, food forests, edible gardens. Agroforestry, growing crops and trees. Together shade grow coffee farms. Hydroponics, growing plants in nutrient water indoor lettuce systems. Aquaponics, hydroponics and fish farming. Fish water feeds plants. No-till farming, minimal soil. Disturbance, grain farming with minimal plowing.